Today we'll study yet another very important, at the same time very logical topic, and that is conic sections. Now the first question that comes to our mind is, why is it called a conic section? And for that what we'll do is, we'll take up a double cone. So this dotted line, it is called as this axis of double cone. And then we have this line which we call it as generator. And if we'll rotate this line by an angle 360 degrees, then we'll get this double cone whose half angle is alpha, and this double cone, it is extended infinity up and infinity downwards. Now what we'll look at is, we'll look at intersection of this double cone with a plane. So we'll look at different possibilities. So if I take a plane which makes an angle 90 degrees with axis of this cone, then in that case, so suppose I'll take this plane which is perpendicular to this axis. So now in this case, section of this intersection will be a circle. So in this case, we'll end up getting a circle. Now if we'll take another plane which makes some angle theta which lies between alpha and pi by 2, in that case, so suppose I take another plane which makes some angle theta which is greater than alpha but less than pi by 2. In that case, the section that you'll get is an ellipse. So from the intersection of this plane and this double cone, we'll get an ellipse. Now we'll take up the third case when we'll take up a plane which makes the same angle alpha as that of half angle of this cone. So we'll take a plane which is parallel to this generator. In that case, suppose it is this plane. So then we'll get parabola. So if theta is equal to alpha, then we'll get a parabola. And if theta is less than alpha, now in this case, this plane, it will intersect this cone in two parts, and in that case we'll get a hyperbola, or we'll get actually two branches of a hyperbola. So in this case we'll end up getting a hyperbola. So because we are getting all these sections from intersection of a plane with a double cone, that is the reason we call it as a conic sections. So in conic sections we'll get an ellipse. Now basically circle is a special case of an ellipse. Then we have parabola, and then we have hyperbola. So basically in conic sections we are interested in three kind of curves. So there are ellipse, parabolas and hyperbolas. Now through the intersection of this plane and this cone, we'll also get some other curves, and which is called as degenerate conics. So if this plane, it passes through this vertex of double cone, in that case we'll end up getting degenerate conics. So if this plane makes an angle 90 degrees and it passes through this vertex, in that case we'll get a point, or essentially a point circle. If we'll take this plane when it makes an angle alpha, but then it passes through this vertex, so then in that case that plane, it will be tangent to this double cone. In that case we'll end up getting a straight line. And if theta is less than alpha, and if it still passes through vertex of this double cone, then we'll end up getting pair of straight lines. So from this intersection of this plane and double cone, we may also get point, line and pair of straight lines, which we call degenerate conics. So we are not interested in degenerate cases. So we are interested in studying parabola, ellipse and hyperbola. So from the sections of this double cone, we know that we have to study parabola, ellipse and hyperbola. Now we look at their formal definitions. So in each of this parabola, ellipse and hyperbola, we always have three things, and they are a fixed point, and this fixed point is called as focus. So we'll always given a fixed point and we'll say that fixed point is a focus. Now in case of a parabola, there is only one fixed point and we say that is focus of a parabola. In case of an ellipse and hyperbola, we have two fixed points and they are called as foci, which is plural of focus. Then we'll have this fixed line, and this fixed line is called as directrix. So again in parabola there will be only one directrix, but in case of an ellipse and hyperbola there will be two directrix. So for parabola we have one focus and one directrix, and for ellipse and hyperbola we will have two foci and two directrix. Now any point on this conic section, whether it is parabola, ellipse or hyperbola, it is at some distance from this focus, and suppose we say this distance is PS and the distance from this fixed line is distance from directrix, and that is PM. So the third thing that we will have in any conic section is ratio of this distance, which is PS upon PM, and ratio of distance of any point from a fixed point and fixed line is also constant, and this ratio is called as eccentricity. So this point is fixed, this line is fixed, and distance of any point on these conic sections from focus and directrix, their ratio, it is also fixed, it is also constant, and this ratio is called as eccentricity. So if we'll draw any figure, whether it is parabola, ellipse or hyperbola, then in that case we'll have this definition, which is PS equals EPM, where PS is distance from fixed point and PM is distance of this point from this given fixed line, and this ratio is always constant, and this ratio is called as eccentricity of this conic. Now depending on this value of E, we can differentiate between the three curves. So if E is equal to 1, in that case we'll have PS is equal to PM, that is distance of any point in parabola will be same from focus and directrix. So that is any point in parabola is equidistant from focus and directrix. So in this case, we'll get a parabola. If the value of E lies between 0 and 1, in that case, PS is less than PM. So this point on the curve will be closer to focus than the directrix. So in that case, we'll get an ellipse. And this third case, when E is greater than 1, in that case PS is greater than PM, then the curve that you'll get is a hyperbola. So depending on this value of E, so when E is equal to 1, we'll get a parabola. If E lies between 0 and 1, we'll get an ellipse. When E equals to 0, we'll end up getting a circle, and circle is a special case of an ellipse. And when E is greater than 1, then we'll get this as a hyperbola. So any conic section is this relationship, which is PS equals EPM. So what is the definition of any conic section? So definition of any conic section is locus of a point P whose ratio of distances from a fixed point and a fixed line is constant and is equal to E. So in case of parabola, what is the standard definition of parabola? The standard definition of a parabola is locus of all the points which are equidistant from focus and directrix. So this is how we formally define conic sections. Now this definition, it is also used to write general equations of conic sections. Say for example, suppose I say, write the equation of a parabola whose focus is say 1, 2 and whose directrix is x plus y equals to 0. So we are given this fixed point and we are also given this directrix. So now we know that any conic section can be identified with three things: fixed point, fixed line and eccentricity. And we know that in case of parabola, eccentricity is always 1. So we know that definition is PS equals EPN. So we have to find the locus of this point P. So what we'll do is we'll let PS alpha comma beta. So PS is nothing but distance formula, distance of this point from this given focus. So it is alpha minus 1 whole square, beta minus 2 whole square. And what is E? In case of a parabola, value of E is 1. And what is PN? PN is distance of this point from this given line. And we know that this distance is alpha plus beta upon root 2. So if I'll square it, I can write it as alpha minus 1 whole square, beta minus 1 whole square, alpha plus beta whole square upon 2. So now I'll change alpha into x and beta into y. So equation of this parabola will be 2x minus 1 whole square plus, so it is y minus 2 whole square, and this is x plus y whole square. So that is the standard equation of this parabola. We can simplify it also. I can write it as 2 times, and this is x square plus 1 minus 2x plus y square plus 4 minus 4y, and this is x square plus y square plus 2xy. So we take everything on the left hand side, then we can write it as x square plus y square minus 2xy minus 4x minus 8y plus 10 equals to 0. So that is the equation of this given parabola. So if we are given the fixed point, if we are given a directrix, and we are also given eccentricity, then simply using PS equals EPN, we can write general definition of any given conic. In the previous section, it can be noticed that any general equation of a conic will be a second degree equation in x and y. So any general equation which is ax square plus 2hxy plus by square plus 2gx plus 2fy plus c equals to 0, this equation, it may also represent a conic. Now we have already studied this equation in pair of straight lines. So in pair of straight lines, what we generally do is we'll find this determinant delta, which is this diagonal ABC, and then H, G, and F. And if this delta is equal to 0, then in that case we always say that this equation will represent a pair of straight lines. So if we have second degree equation, first we'll find its delta. If delta is 0, then this equation will represent a pair of straight lines. So they may be imaginary lines or real lines. Now, when delta is unequal to 0, in that case, we'll compare h square and AB. If delta is unequal to 0 and h square equals to AB, in this case, this equation, it will represent a parabola. If delta is unequal to 0, but h square is less than AB, in that case, this equation, it will represent an ellipse. And if delta is unequal to 0, but h square is greater than AB, in this case, this equation, it will represent a hyperbola. So this equation, if delta is equal to 0, will represent a pair of straight lines. If delta is unequal to 0, but if h square equals to AB, we'll get a parabola. If h square is less than AB, we'll get an ellipse. And if h square is greater than AB, we'll get a hyperbola. So let us take up a question, which is the equation 16x square plus y square plus 8xy minus 74x minus 78y plus 212 equals to 0. This equation represents what? So what I'll do is I'll compare it with the standard equation. So the value of A here is 16, B is 1, H is 4, G is minus 37, F is minus 39, and C is 212. Now first we'll calculate this delta, and which is ABC, so it is 16, 1, 212, and then H, so which is 4, 4, G, that is minus 37, and F, which is minus 39, minus 39. Now what I'll do is I'll write R1 as R1 minus 4 times R2. So if I'll write it, I'll write this delta as, so it'll be 16 minus 16, 0, 4 minus 4, 0, and there'll be minus 37 and plus 4 into 39, and here I'll get 4, 1, minus 37, minus 39, minus 39 and 212. So if I'll expand it about first row, I'll write minus 37 into 4 into 39, and then if I'll multiply it, I'll get minus 39 into 4 and plus 37. Now we know that this cannot be 0, and this number, it also cannot be 0. So this delta is actually unequal to 0. So this equation, it doesn't represent a pair of straight lines. So now next thing, I'll find h square. H square in this case is 16. We'll also find a into b. So value of a into b is 16 into 1, which is 16. So here I'll get h square equals to ab. So when delta is unequal to 0 and h square equals to ab, then this equation, it represents a parabola. So basically, it has a second degree equation of a general parabola. Now we'll take another question, and this question, it was asked in IT JEE, and the question was, this curve described parametrically by x equals t square plus t plus 1 and y equals t square minus t plus 1 represents what? So basically, we have not studied parametric forms of parabola, but then we know that any equation which is at square plus bt plus c and dt square plus et plus f will always represent a parabola. So without even solving, we know that this equation, it does represent a parabola. Now since we have not studied parametric forms, so we'll solve it by general equation. So what we'll do is, I'll add the two equations. So if I'll add the two equations, I'll get x plus y as 2 times t square plus 1. And if I'll subtract them, I'll get x minus y as 2t. Now what I'll do is, I'll put the value of t here. So I'll write x plus y equals 2 times, and this is x minus y upon 2 whole square, and then plus 1. So I can write it as x plus y, and this is 2, and will be x square plus y square minus 2xy plus 4 upon 4. So I'll cancel this 2. So I'll write it as x square plus y square minus 2xy minus 2x minus 2y and plus 4 equals 0. So that is the general equation of this curve. Now for this equation, what is the value of a? A is 1, b is 1, h is minus 1, g is minus 1, f is minus 1, and c is 4. So again, we'll find this delta. So delta will be ABC. So 1, 1, 4. Now h is minus 1, g is minus 1, and f is minus 1 and minus 1. So again, I'll do R1 plus R2. So I'll write R1 as R1 plus R2. So I'll write this delta as 0, 0, minus 2, and this is minus 1, 1, minus 1, minus 1, minus 1, and 4. If we'll solve this determinant, we'll get it as minus 2, and here will be 1 plus 1, so that is minus 4, which is unequal to 0. So this equation, it doesn't represent a pair of straight lines. So now we'll find h square. H square in this case is 1. And what's AB? A into B is also 1. So it is h square equals to AB. So this parametric equation, it will represent a parabola. So as predicted, this equation, it comes out to be a parabola. In this video, we'll be discussing polar equations of conic section. Now in this polar equation, we are going to treat focus as a pole. So any general point on this conic section, say it is P, it is at a distance r from focus, and it makes an angle theta with the axis. Now we have dropped a perpendicular from P on axis, and then we have drawn a chord perpendicular to axis and passing through focus. This chord is actually called as latus rectum, and half of this chord, it is called as semi-latus rectum. So it is also given that this length QS, it is semi-latus rectum, and its value is L. Now we need to write polar equation of this conic section. So what we know is, we know that in conic section, PS equals EPM. Now PS in this case is simply R. This is E. Now what about PM? I can write this PM as RS plus SM. Now this right angle triangle, I know that this is R and this is theta. So this Sn is simply R cos theta. So I'll write it as R equals E and then RS plus R cos theta. Now we need to find this RS. Now this RS is equal to this distance. Distance of this point Q from directrix. Say this is M1. So again this point Q, it lies on conic section. So we can write it as SQ equals E Q M1. Now SQ in this case is semi-later septum, so it will be L. So I can write Q M1 as L by E. So this length RS is actually equal to L by E. So I can write this equation as R equals E and RS is L by E and plus R cos theta. So I'll multiply this E inside. So I'll write R equals L plus R E cos theta. So I'll take this R on the left hand side. I'll write R 1 minus E cos theta equals L, and this is R equals L upon 1 minus E cos theta, and that is the polar equation of conic section taking focus as its pole. So in this case again, when E is 1, it will represent a parabola. If E is less than 1, it will represent an ellipse, and if E is greater than 1, it will represent a hyperbola. So this is how we are going to write polar equation of conic sections. Now in case of a parabola, we know that value of E is 1. So in case of a parabola, we can simply write it as R equals L upon, and 1 minus value of E here is 1. So it will be simply 1 minus cos theta. So we'll use half angle formula. So it is L and it is 1 and 1 minus 2 sine square theta by 2. So we can write it as R equals L by 2 cosec square theta by 2. So that is the equation of parabola in polar form. So we can write equation of conic sections in rectangular form, and we can also write polar equations of conic sections. Now when we'll be dealing with problems related to focal chord and their focal distances, in that case I'll be using polar equation of conic sections.